and away we go. Okay, I can take that away. Keep it handy for future days. I want to start today with kind of an off-the-wall problem. This is a classic, actually. It's used in a lot of classes, but we have a piece of ice sitting on top of a hemispherical igloo, and you replace the block ever so slightly, and it begins to slide down the igloo. At what point will it lose contact with the surface of the igloo? And we assume zero friction. So I'm going to start by making a simple sketch of this situation. Here's the ground level. There's the center of the igloo, center of curvature for the igloo. And let's see, we'll probably have to slide this down a little bit first. I think it's still showing. All right, that kind of works for a sketch of the situation. So imagine that we have this block of ice that's up there on top of that, and it gets nudged ever so slightly and starts to slide down this thing. And so at some point, it might be down here, and this would be the block of ice. And at that time, it's going to be at an angle theta there. Okay, and things we might have to think about are the height of that above the ground level. And if capital R is the radius of the igloo, then R divided by capital R will equal this thing. I think this is going to look like R sine of theta, because that'll be the height. Okay, we actually have to start with a free body diagram on this thing. And if I kind of try to reproduce that angle there, if this is the center of the free body diagram, the two forces acting will be the normal force and then mg downward. And if I select a coordinate system that is instantaneously like this, it's going to be changing throughout the downward path of the thing. But if that's the x direction, and if the normal force is pointing in the y direction, you might be able to do something with that. And I can split the gravitational force into two components, and one that's perpendicular to the surface of the igloo and opposite the normal force, and another one that's on the surface of the igloo. And let's see about this angle. Is that, let's see, this is theta. This will be 90 minus theta. This will be theta again. And this would be 90 minus theta. But if we measure this, this would be theta again. So the we'll have over here is going to be mg sine of theta, because it's opposite that angle theta. Component down here will be mg cosine theta. And it makes a little bit of sense, because here we've got an angle close to 90 degrees. And here we have that same angle close to 90 degrees. So anyway, this is mg sine theta over here, and this is mg cosine theta. If I try to do a Newton's second law problem on here, I would start off with the sum of the forces in the y direction are going to be zero, because the acceleration is going to be in the x direction. And what I'd have is n minus mg sine theta in that direction, and those will be 0. The sum of the forces in the x direction, that's tangential to this thing, are what are going to produce a tangential acceleration in this case, and I'm just going to call it ma sub t, and there's only one force, and it's that mg cosine of theta will equal m times the tangential acceleration. So we've dealt with situations where we've had either 0 acceleration or constant acceleration. Here we have one that's going to be changing continually as we drop down there. And actually, this isn't equal to 0. The normal force minus mg sine theta, as soon as this thing starts to move, it's going to have a centripetal acceleration toward the center of the path. So this will actually be minus mv squared over r, and that'll be ma for that block of ice. And it's got a minus sign because I chose y to be positive way, and the acceleration is going to be in that way. But when the normal force, or when it loses contact with the surface of the igloo, the normal force is going to drop to 0. And if I just write an expression for the normal force, it's going to equal mg sine of theta, I brought that to the other side, minus mv squared over capital R. Now, v is going to be continually increasing. Sine of theta is going to be decreasing as it slides down here. So this term will be getting smaller. This term will be getting bigger. And eventually, this term will equal that. And at that point, the normal force will go to 0. We won't have a sufficient mg sine theta, won't be big enough anymore to hold this thing down onto the igloo. So it's kind of a complicated situation, but that's what we have in this case. So the normal force vanishes when mg sine theta is going to equal mv squared over r. Or just g sine theta will equal v squared over r. But to figure that out, we'd have to deal with the tangential acceleration that's varying with the cosine of theta. And to know what the speed actually is, we'd have to integrate something from 0 to some later value when this happens to be the case. And we don't have the tools for that yet, but we can solve this using energy conservation. Now, here's what we'll do for energy conservation. We'll figure the initial energy is going to equal the energy throughout. With no friction, we don't have any energy loss. And energy later will equal initial energy. The later that we're interested in is when this condition here happens to be met. So what will the initial energy be? Well, it's going to be gravitational potential energy that this block of ice would have at the very top. That's all there is. And it's just going to be, if we let U grav, and I'll use that, be 0 down here at the ground level, then capital mgr will be the initial energy that we have. Well, what happens to that energy later? Well, as it slides down the thing, it loses gravitational potential energy, and this will be its height at a later time. It's going to still have some gravitational potential energy, mg r sine theta, but it's also going to have some kinetic energy now, and we'll just call that 1/2 mv squared. So this is the energy as a function of the angle theta is actually what it depends on, but it's also going to depend on the speed, and we don't quite have anything for that here, except I have the condition when it leaves contact with the igloo, and it is that mg sine theta is going to equal mv squared over r. Well, if I multiply out from underneath there, at the instant that it loses contact, this is the condition we'll have. mg capital R sine of theta will equal mv squared. Well, that's mgr sine theta. I can replace it with mv squared because that's what mv squared will be when it loses contact. And so now I can say mg capital R. I could divide out all the m's, I guess, but that will equal mgr sine theta, which is mv squared, or actually what I think I'll do instead, I want to know the angle theta. mv squared is going to be this thing, so I'll stick that in there instead. So mg capital R sine theta plus 1/2 of mv squared, or 1/2 of mg capital R sine theta. And there's my expression for when this happens. First thing I'm going to do is get rid of all the m's, because it doesn't matter what the block of the ice cube is. And here I'll have gr sine theta plus 1/2 gr sine theta. That's 3/2 gr sine theta. This weird little problem will end up being 3/2 g capital R sine theta. If I divide both sides by gr, I'll get 1 is equal to 3/2 times the sine of theta, or the sine of theta is equal to 2/3. And now it's just a matter of the inverse sine of 2/3, that's a -1 there, is equal to theta. And whatever the inverse sine of 2/3 happens to be, oh man, when I calculated this, I wrote it down so sloppily I can't even read my writing. I get about 42 degrees. Let's see. Who knows what kind of significant figures we've got on this thing. Actually, it would be 41.8 degrees to 3 sig figs, but since everything was in terms of letters, we can't say. Anyway, weird little problem there. And we could only go so far with Newton's law considerations. We don't have the tools yet. If you've taken second quarter calc, you might be able to solve this thing, or let's see. Yeah, I'm not positive at what level in calculus you do that, but there we did it. Okay.
Hey, Professor.
Yes.
So on that last problem, are we able to, so on the left side, when you divided by your mass to cancel out mass on both sides, could we just divide by the whole expression on the left and apply it to the whole equation?
Yes, you could. So you
Like,
could
look,
divide by mgr, because there's an mgr in every term as well.
okay, sweet.
Yeah, then you would have had 1 is equal to wherever it went.
It'd be sine theta plus 1/2 sine theta, and then we could combine
Oh,
that to get that. Just to
yeah.
simplify it a little bit faster.
Yep, it would. So
All right,
that would have
thank you.
worked. Okay. Here's another one. Let's see. This is, so far I'm dealing with friction-free situations, and a little later today I'm going to start doing some that have friction in them. So It will be kind of interesting. Anyway, we've got a spring in a vertical position with a lightweight platform attached to it. So we'll just imagine that got a spring sitting here like this, and it's an ideal spring. It could be compressed or raised, whichever we want to do it. Spring constant is 7.53 newtons per centimeter. We have a block of mass 3.32 kilogram, and we drop it from 1.85 meters above the platform. So right now the spring is in its equilibrium position, and we can define X to be 0 right there, and we'll say X is positive upwards. And this block starts from rest here, and 3.32 kilograms. And it starts off 1.85 meters above this thing when it's dropped. So the first question asks, how fast is it moving when it contacts the platform? Well, we can do that with conservation of energy. We can also say that U grav is going to equal 0 at this point. So this is our 0 point for gravitational potential energy. It's also our 0 point for spring potential energy. So let's see what we get out of here. I'll call this H initial. So with energy conservation problems, the initial, well, didn't spell that very well, will equal the final. And initially, all we have is gravitational potential energy there. So whatever the mass is, there it is. mg H initial is our initial energy. When it first contacts the platform here, all it's going to have is kinetic energy, because it's down at the level where gravitational potential energy is 0. So it's just going to be 1/2 mv squared. And turns out it doesn't matter the mass of the block for this part, at least. So we can cross those out, and we'll get that v squared is going to equal 2g h sub I. And we can plug in the numbers if we want. Well, 2 times 9.81 meters per second squared times the h sub I, 1.85 meters. And then take the square root of that, and I'm going to do them both at the same time. And I get about 6.0. Let's see, we've got 3 sig figs, so 6.03, maybe 6.02, I can't tell on my calculator, but meters per second for the speed when it first contacts that thing. So we have that. And then how much will the spring be compressed when the mass is brought to rest? Okay, this one's going to be a little bit trickier. But still, we'll use conservation of energy. Initial is going to equal final. Now, I could use this speed here and start over with a new initial situation where I could call this time 0, or since it's still going to be the same amount of energy, I could say that this amount of energy will equal the energy that we have at the end when we don't have any kinetic energy. We already know that this happens to be true, but for this new initial equals final, I'll have mg h sub I and that's the initial energy that we have, will equal, well, let's see, we're going to compress the spring by some amount, x sub c maybe. So we'll have some spring potential energy. It's going to be 1/2 k x sub c squared. We'll have that, but we're going to have some negative gravitational potential energy. I'm going to let x sub c equal the magnitude of the compression, which means it won't have a sign on it, but I can assign a sign to it. We're going to be below the 0 point for gravitational potential energy. And when that's the case, we'll have negative potential energy. You can do that for gravitational potential energy, have negative potential energy, just put your mass below the 0 level. Like if it's ground level, dig a hole and drop the mass in there, and it's got negative gravitational potential energy. But in this case, that will be minus mg x sub c. And so that's the situation that I have here. Now, this time I cannot drop the mass out of the situation because, let's see, oh, this term doesn't have mass in it. So that's going to make things a little bit complicated. Is there anything else I can drop out? No, I can't simplify this thing very well, but I can rewrite it. So I'll have 0 is going to equal 1/2 k times x sub c squared minus mg times x sub c minus mg h sub I. And this is just a number. I know the spring constant. This is just a number. That's the weight of the mass. And this is just a number. And so I've got a quadratic equation in x sub c, and I have to solve it using that. So I'm going to have to figure out these numbers. 1/2 k is going to equal, I think I'll have to convert this to newtons per meter. 7.53 newtons per meter or centimeter times 100 meters per meter, and it'll be 753 newtons per meter. No surprise there. mg, I can figure out that. At this point, I'm just doing some arithmetic here. And mgh sub I, I'll just take this and multiply it by that initial height. And I have 6.03. And that will be Newton meters. Okay, this is going to be a little bit scary here, but here's what we'll have. I'll have 1/2 k, so I need to take that 753 and divide by 2. And I get about 377 newtons per meter times x sub c squared. Okay, now x sub c is to be measured in meters. And so when we square it, we'll get meters squared, and newtons per meter times meters squared will give us Newton meters, which are joules. So this is energy. mg is newtons, so 32.6 newtons times x sub c. I am not going to try to hang on to these units when I'm plugging this into the quadratic equation, but it will work out. And then minus 6.03 Newton meters for the mg h sub I. Okay, I can plug those straight into the thing on my calculator here. Let's see. I think I click program, and then quad is the one that I wrote that I stuck in here. And I just enter to run that. So the x squared term, 377. The b term is minus 32.6. And minus 6.03. And to get those minuses on there, I have to use that. And I get root 1 is 1.769 or 0.177. And the other root is negative, and it would be, let's see, up in this direction somehow. We're not interested in that root, but this will equal, 0.177 meters. So it'll be compressed by, this is actually a fairly stiff spring, 753 newtons per meter. So we'll compress it by that much. But this was an energy conservation problem. I actually had to consider two types of potential energy here, and we haven't had to do that yet. We've also not had to deal with negative potential energy before. So a bit more complicated than some of the problems we've done. Still friction-free though. Here's one other friction-free problem. The mass is attached to a spring with a force constant of 775 newtons per meter. The spring is then stretched to 23 or by 23.0 centimeters. And forgot to mention that we let go of the mass at some point, and we want to determine the maximum speed of the mass. So here's the situation. Imagine this is a horizontal surface. We've got this would be the equilibrium position of the spring, and x is 0 at that point, but we've stretched it past that and attached this mass to it. I forgot to give you a mass. Let's see. I just made up this problem this morning, so let's see. 1.75 kilograms. How's that? Okay. And this amount of stretch is 23.0 centimeters or 0.230 meters. Let's see which one we have to have. Okay, well, initially, the only energy we have is a stretched spring, and when it pulls back to the equilibrium position, the only energy we're going to have is kinetic energy of this thing. The spring at this point won't be compressed or stretched. Now, next quarter, we'll study situations where this thing goes past that point and compresses the spring and just bounces back and forth for a while, especially if we have no friction. But for here, I'll just say initial equals final. This is for part A. And all I'll have is that 1/2 kx squared is going to equal 1/2 mv squared. So I can drop the 1/2. K, 775 newtons per meter. newtons per meter times 0.230 meters squared will equal the mass, 1.75 kilograms times some V that we don't know. That's what we're trying to figure out. Okay, well, all I have to do is divide both sides by this and do the multiplication and take the square root. So V will end up equaling 775 newtons per meter times 0.230 meters squared, and I have to divide by the 1.75 kilograms and take the square root of the whole thing. So a newton per meter times a meter squared is a newton meter, and that's a joule, but it's also a joule is a kilogram meter per second squared. And if I divide by kilograms, just kilogram meter squared per second squared divided by kilograms is what I'll have under the radical. And it'll end up meters squared per second squared. When you take the square root, you just get meters per second. So unit-wise, everything works. So okay, I get 23.43 before I take the square root, and then square root of that is 4.84 meters per second. So that's the speed when the thing is pulled back to the equilibrium position. Part B asks, determine the speed of the mass when it is 8.00 centimeters from the equilibrium position, and ignoring friction. Okay, well, at that point, this will be part B. We're going to start with the same initial energy, 1/2 kx squared, and I'll call it here 1/2 kx initial squared, and that'll be that 0.30 meters. And that will equal, if we're only partway back to this thing, we'll have a combination of spring potential energy and kinetic energy. So we'll have 1/2 k x final squared plus 1/2 mv squared. So we have virtually the same equation to solve we did before. We just have to subtract the off of there. Okay, so let's see. Everything's got a 1/2 in it. I can drop those. I'll have kx initial squared equals kx final squared plus mv squared, and kx initial squared minus kx final squared equals mv squared. I can factor that k out of here. May not make much difference, but and divide both sides by m, and that will equal v squared. So v will equal a great big square root here, k, which is 775 newtons per meter, times x initial was the 0.230 meters, squared, minus x final is 8 centimeters, which is 8.00 times 10 to the minus 2 meters, and I have to square that. And then that ends off those parentheses, and divide by the mass again, 1.75 kilograms. So just plug and chug here. But the key point on this was we had to be able to write an expression that included the initial energy, and then we had two different final energies here. We had a spring that was still stretched, so we had to have an expression for its potential energy there. And this is almost more work to calculate than it's worth, but go ahead and do it. Let's see. Yeah, I think this will work. I hope that does it right. Okay, I get 4 point, I get virtually the same energy that I had before, which doesn't surprise me too much. It's almost all the way back to there, and that last little chunk of pulling the spring back isn't going to add that much to the energy because remember the energy that's stored by a spring is this triangle here. And we started off over here at 23, and now we're only down to about a third of that distance. So this little triangle here isn't going to be all that large compared to this thing. And I do get virtually the same number. I get to three significant figures. I still have 4.84 meters per second. This one was 4.840. This one is 4.837. And so you can't tell the difference between the two with the number of significant figures we have. But this should be a slightly lower speed than this one. And so it just doesn't go up in the sig figs. Okay. Now I've got some that I want to introduce friction on, and we can do just a couple of these. This is one that I actually had on a test at one time, and it's kind of weird in that a mass is attached to a spring and you compress the spring, and in this region right here there's no friction, but then it reaches a point where there is friction out here, so it's kind of an artificial situation in that regard. But what have we got? How far beyond the equilibrium position will the mass slide before stopping? Okay, so we want to think about that. In this case, once the mass is back to the equilibrium position, we'll be interested in knowing what the normal force is, and to no surprise, there will be friction to the left once it enters that one region. So there will be a kinetic friction force. There will be a normal force upward and mg downward. Nothing's going on in the vertical direction. So the sum of the forces in the y direction, with positive being upward, is just going to be n minus mg equals 0. So the normal force is just going to equal the weight in this case. No surprise there. How far past the equilibrium position will it get before stopping? Well, this is our first, quote, energy conservation problem we've done where energy is not completely conserved. I think you can still read that. And here's what we'll have. I just think of these as this: initial energy minus energy lost. Where's the energy lost to? To friction. And actually, as far as the universe is concerned, there is no energy lost. That frictional energy goes to heating the bottom of the block and the top of the surface. And if you measured that heat energy, you could have it included as part of the energy balance. But in this case, we'll have it's lost as far as kinetic or potential energy is concerned. And minus energy lost is going to equal the energy final. But it comes to rest at the end and the spring is no longer stretched. So this is going to equal 0. So what we're actually saying is the initial energy minus energy lost is 0. Okay, well, we can figure out that. We just have to figure out how much work is gravity going to do. So in this section here, if we start our watch right here, well, actually, we can start it over here when we've got the spring that's compressed by this amount. And, oh, it's initially compressed the distance d from its equilibrium position. So this is capital D right here. So the initial energy we have is going to be 1/2 k times d squared. When the mass gets back to here, it's going to have an amount of kinetic energy that's 1/2 mv squared, but no energy has been lost yet because there wasn't any friction in this area here. So we won't have to worry about that. But the final situation is going to be equal to 0. And what happens is once we get out here, and maybe the block ends up over here, we've moved a distance x out onto this thing. And friction is going to be doing work on that thing all the way out here. Well, or from here all the way out to here. The frictional force will be mu sub k times n, and x is the distance over which it acts, and this will represent the energy lost to friction. Now, we know that the normal force is equal to mg in this case, so we can say 1/2 k d squared minus mu sub k mg x. Okay, force times displacement is the work, and it's negative work that's done by friction. That will equal 0. Then we can kick that across. 1/2 k d squared equals mu sub k mgx. And we just want to know how far it goes. So just divide both sides by mu sub k mg, and we'll get something that looks kind of incomprehensible. Kd squared over 2 mu sub k mg. But that's what it ends up being. So let's see. The distance traveled is inversely proportional to the mass. So the more mass you have attached to this thing, the less far it will go. Okay, you could think of a couple reasons for that. The more mass you have, the slower it's going to be going when it gets back to this equilibrium position. And the greater the normal force will be, so the more energy is lost to friction when that's the case. So 2 reasons that the distance is inversely proportional to the mass. Okay, this thing asks, what is the speed of the mass when it is a distance d to the right of the equilibrium position? Okay, well, we can do an initial energy minus energy lost is equal to the final energy. And see if this works. Okay, we started off with this much energy, 1/2 kd squared. Now, instead of some unknown distance x, it's going to be a known distance d. And so the friction that's stealing energy from this system is going to be mu sub k times n times d, but n is equal to mg. So mg times d. So here's the initial energy minus the energy lost to friction. Now remember, the mass gets slid over this distance, but there's no friction in this region. And then it enters this stuff over here, minus mu cd, and that'll equal the final kinetic energy when it's this distance d over here. Actually, it won't be x this time, it'll be d. So there will be some speed here. Okay, well, oops, got an m in here. 1/2 mv squared, it equals that kinetic energy that it has there. So initial energy minus energy lost equals the kinetic energy at that point over there, which maybe the friction is so great it won't even reach that distance. And we'll see that in the expression that we solve for. Solving this for v, I'll get multiply both sides by 2, and I'll have kd squared minus 2 mu sub k mg d. And this time I won't have to worry about solving this, but that will equal mv squared, divide both sides by m, and I'll get k over m times d squared minus 2 mu sub k g, I think. Let's see, divided by m. Yep, equals v squared. And v is equal to the square root of k over m times d squared minus 2 mu sub k g times, whoops, I lost a d here, mu sub k times d. Okay, it's possible that this thing ends up being negative, and an awful lot is going to depend on the relation between k and m. If m is too big, then k over m times d squared, this term could be smaller than this term. And if that's the case, you'd be getting an imaginary number for the speed of this thing. So it's actually possible, if we made up particular numbers, that the mass would never get to that distance, that it would stop before it gets there. And that's what that thing would tell you. However, that's the expression that tells us how far it gets to, which also depends on k over m. And you might be able to come up with something for the exact condition under which the thing would never reach the distance d. Okay, let's see, do we have another one? Okay, this one's really complicated. Might almost save it for Monday, but let's have a look at it anyway. We have a wooden block with a mass of 1.50 kilograms placed against a compressed spring at the bottom of an incline of slope 30 degrees. Holy smoke. Couldn't make this much more complicated than this. So we'll just imagine that, oh, I probably got an angle greater than 30 degrees, but ignore that. So down here, let's just suppose this is 30.0 degrees, and we'll call that theta. And we've got this spring that's compressed here. let's see, this is just a platform at the end of the spring. And then we've got this mass that's set against it. And the spring is compressed. Let's see, when the spring is released, it projects the block up the incline. So we've got this thing compressed. We set the mass against it. We let go, and the mass is going to hit up the incline at the point B, which is up here somewhere. Oh, we'll call this point A. And then point B is up here somewhere, 6 meters up the incline from A. This must be a really long incline, and it must be a pretty strong spring to be able to launch this thing up there. It's still moving up the incline at 7 meters per second. Holy smoke. And is no longer in contact with the spring. So the spring would push back to its equilibrium position and then stop pushing. And the mass just keeps heading on up there. The coefficient of kinetic friction between the block and the incline is mu sub k equals 0.50. Holy smoke. Calculate the amount of potential energy that was initially stored in the spring. Well, this is an energy conservation problem, but we've got friction. So we're going to have to say that 1/2 kx squared, which, are we told how much it was stored? No, we don't know. So this is just going to be this is what we're after actually, minus E lost will equal E final. Okay, this is very rough. And I just made an assumption when I wrote this down, and that was that the initial position of this thing is where gravitational potential energy is equal to 0. Because we've got a thing that's going to be going uphill, it's going to be rising, so it'll be gaining gravitational potential energy, and my expression will just be easier if I set it gravitational energy equal to 0 here. So initially, all I have is spring potential energy. Okay. Now that final energy, we're going to have no spring potential energy. Okay. This mass got released from the spring, and so the spring isn't compressed anymore. But it will have some gravitational potential energy, U grav, which isn't going to be quite so simple. But it will also have some kinetic energy up there. So 1/2 mv squared. Actually, this problem isn't as bad as I thought. There's another one that's similar to this where you've got friction on a plane, you let a block slide down the plane, hit a spring, compress the spring, and you try to figure out how much it compresses the spring. And then later, you try to figure out how much or how far the mass will go back up the plane when the spring pushes back on it. So that one's worse, but this one's not so bad. The complicated part will be finding the energy lost and also the gravitational potential energy. But that one's not so bad. If it's 6 meters up the hill there, if this is 6.00 meters and it's a 30-degree angle here. Well, this height that it moves up there, h over 6.00 meters is going to be the sine of 30 degrees, opposite over hypotenuse. So h will equal 6.00 meters sine of 30. I can do that in my head. Equals 3.00 meters. So I can use that for the U grav. But what about the energy lost? Okay, have to draw a free body diagram. I'll have mg acting downward. I'll have the frictional force when it's going uphill. It's going to be kinetic friction in that direction. And I'll have a normal force. Okay, now I'm not going to be using Newton's laws. So the only reason I care about this thing is because I want to know what the normal force is. Okay, this is theta. This is 90 minus theta. This is theta again. And mg is that way. The component that is into the plane there is going to be mg cosine of theta. So the normal force will equal that component. So N is going to equal mg cosine of theta. Okay, which means the frictional force, which is mu sub k times N, is going to be mu sub k mg cos theta. The energy lost will equal that force times the distance over which it acted. Well, the block slid up the hill by 6.00 meters. So the energy lost, I'll have 1/2 kx squared minus the magnitude of the frictional force, mu sub k mg cosine of theta, which is 30 degrees. And I multiply that by my 6.00 meters. And that'll be the work done by friction. And we take that amount away from the initial energy that we started with. And I'll end up with, let's see, this is an H here, not an N. That'll equal M times G times 3.00 meters plus 1/2 mv squared. So what we're actually at here is the 1/2 kx squared. It's just asking the amount of energy stored in the spring. So this is all I want. I don't have to do a bunch of too much rearranging, but I'll have that 1/2 kx squared will equal mu sub k mg cos 30 degrees plus mg times 3.00 meters plus 1/2 times m times v, which is 7 meters per second. And we square that. Okay, here I could factor out an mg, and 1/2 kx squared will equal mg times mu sub k cos 30 plus 3.00. Did I lose something on that one? Yeah, I lost my 6 meters. Where'd it go? Okay. Pretend you didn't see that mistake. Anyway, now we can plug in numbers here. That will equal whatever the mass of that thing was, 1.50 kilograms times 9.81 meters per second squared. Let's see if our units come out right. Mu sub k is 0.50. It's dimensionless. 6.00 meters times cosine of 30, which is also dimensionless, plus 3.00 meters. So what'll we have? We'll have kilogram meters per second squared times meters, which makes it kilogram meters squared per second squared. Those are joules at least. And then somewhere on here, I forgot to write down my 1/2 mv squared. There we go. Okay, plus 1/2 times 1.50 kilograms times 7 meters per second squared, or meters per second quantity squared. Okay, this will be joules, that's joules. Unit-wise, we're just fine. And so all you'd have to do is multiply all this stuff out together without making a mistake, and you'd get the value. So I'm not worried about that. We're just about out of time here. But this was a complicated energy conservation problem, and that's one of the first ones we've had to deal with energy lost there. So tomorrow, I want to do a few more conservation of energy problems or energy problems where we'll have energy lost to friction. So we'll take a look at those things. Are there any questions so far? I did already set up homeworks 3 and 4 so that you can resubmit your assignments on those. Take a look at what you submitted, and if it's not up to snuff, you have the ability to replace those and upload a new assignment. So do that. And when you make a PDF of something, first thing you should do is send it to yourself and make sure it's very legible. And if it's not, figure out a way to do it better. Your phone will make good PDFs. White paper, I think. It seems like when people are using tan paper, it's just not coming through very well. And this is a Uniball Vision Elite. I think the ones I buy are, these are the ones that are bold, and they seem to work very well for making PDFs from. So something else to be thinking about anyway. All righty, we are done for the day, I think. So I'm going to stop the share and end the meeting in